The next and the final keynote speech is from Professor Peter Tenberge. Hello, Professor Tenberge. Good morning. Since 2012, Professor Tenberge is the chair of Industrial and Automotive Drivetrains at Ruhr University Bochum. He had previously served as professor for machine and elements at Chemnitz University from 1994 to 2012. Before he was professor, he worked in automotive industry in Schaeffler and ZF. Professor Tenberge has proposed for automotive applications several transmission concepts for AT, DCT, CVT, and hybrids. And in 2012, he was awarded the SAE Timken Howard Simpson Automotive Transmission and Driveline Innovation Award. The topic of his keynote speech is multi-mode drive system for Pedelecs with more ratio, more torque, and more boost power. Hello, Professor Tenberge. Can you catch me? Good morning.
I can hear you, but I have a very weak connection.
Yeah, good morning. Now it's your turn. Would you like to see something first and then we play your video, or we play your video directly? Okay, let's play. 放他的录像吧，好吧。
Ladies and gentlemen, welcome to my speech about new multi-mode drive systems for Pedelecs. This paper is about two new drive systems for Pedelecs which are split onto a crank unit and a hub unit and which do not need any additional multi-speed transmission or continuously variable traction transmission. In a full version of this drivetrain for trekking and cargo bikes, the first electric motor E1 in the crank unit supports the crankshaft. The second motor, E2, in the hub unit controls the transmission ratio, but can also boost the bike in most of the driving situations. In the light version of this drive system, for example for city bikes with limited top speed, the motor E1 can be omitted because E2 also provides a sufficient electrical boost support. With the following slides, I will explain the market situation of Pedelecs in Europe and especially in Germany, then the design of these drive systems, and finally some simulations to show the advantages, performance of this technology and to show the chances in the market. My name is Peter Tenberge. I'm a professor from Ruhr University Bochum in Germany. For about 45 years I'm working on transmission for any kind of vehicles, and my first contact with this kind of ball split transmission was already in 1981. The market for Pedelecs in Germany has grown in the last 10 years from around 0 to more than 2 million units per year. The annual growth rates have been in the two-digit range for years. More and more customers are opting for these bicycles and like the new driving experience with a so relaxed driving style. During this time, many researchers and developers have enormously improved the power density and the controllability of the drive systems. And year by year, there are always new providers on this market with interesting drive concepts. In Pedelecs, always persons mainly drive the two-wheelers. They apply their drive torques with their feet and via pedals to the crankshaft in the crank unit. Their drive torque is transmitted to the driven rear wheel via an intermediate gear. If necessary, the driving person is supported by a small electric motor, which either operates with a constant ratio onto the output shaft of the crank unit, or which sits in a hub unit of the driven rear wheel and operates there also with a constant ratio onto this wheel. In A, this figure shows an S-pedelec for higher speeds bigger than 25 kph with an electric motor with a peak power of 800 watt in the rear wheel hub and a chain transmission with 11 speeds between the crank unit and the rear wheel. In B, it shows a pedelec with an electric motor with up to 500 watt short-term peak power, which is built into the crank unit and which supports the bicycle up to speeds of 25 kph. This slide shows in A characteristic map of an electric motor for a pedelec with a maximum torque of 4.5 Newton meters and a short-term maximum power of 500 watt. The operating software for the pedelec controls the support power in different operating modes. The standard option are 3 to 5 levels of torque support, always proportional to the driver's torque. A fairly new option is a continuously increasing torque from the supporting e-motor if a pre-selected maximum drive power of the driver is exceeded. That means that the driver can specify which physical load he would like to apply for driving at the moment. The remainder of the current power demand of the bicycle should then be provided by the electric support system. The slide B exemplarily shows two characteristics of a driver's torque capability to perform at 100% or at 50%. A driver can apply very high torques to the crankshaft at low crank speeds. Older and sick people sometimes have completely different performance maps or even different performance maps for their left or right leg. Very sporty drivers can achieve significantly higher levels of performance over longer periods of time. In the current bike market, very different drive systems for a large number of driver characteristics can be found. This slide illustrates the performance of an exemplary pedelec with a total weight of 130 kilograms. In this driving situation, the model driver is ready to stress himself with 100%, which means with a maximum power of 250 watt. The electrical boost should be switched off for now. In this example, the transmission system provides gear ratios between crankshaft and wheel between 1.65 and 0.3. This means that the driver can, for example, drive a nominal crank speed of 60 rpm in a speed range from 5 kph to 27 kph. Below and above the limit ratios determine the crank speed as a function of the driving speed. With this performance of 100%, this driver can climb an incline of 20% up to a speed of 3.5 kph with a pedal speed of 43 per minute, and he generates a wheel torque of 90 Nm. But even at 5 kph, his power is only sufficient for an incline of 13.5% and a wheel torque of 63 Nm at the crank speed of 60 rpm. Such a strong driver can move this bike on a flat road at speeds just below 30 kph. A driver who is only half as strong can only drive uphill an incline of approximately 6% at 5 kph and can only reach a top speed of 21 kph without electrical assistance. These physical relations show when and how much an electrical support system should support drivers who currently want to ride with less physical power. This slide illustrates a possible structure of the drive system of a pedelec with an electric motor in the crank unit and a 14-speed gearbox from roll-off in the hub unit. The rotor shaft of the electric motor E1 lies parallel to the crankshaft and is connected to it via several gear stages with the constant ratios. These gear ratios are in a total range of 25 to 35. A freewheel F2 is located between the electric motor and the output shaft of such a crank unit. This is used to ensure that at speeds above 25 kph, at which in Germany the electric motor is not allowed to support the pedelec, the electric motor can be switched off and has no longer to be dragged along by the crankshaft. Another freewheel F1 is located between the crankshaft and the output shaft of the crank unit, so that the electric motor can alone move the bicycle in a push mode at low driving speeds without the cranks rotating. And two sensors are used to measure the speed and torque on the output shaft of the crank unit somewhere between the freewheels F1 and F2 in order to know the driver's current performance. Plenty embodiments of crank units with an integrated electric motor and also of hub units with an integrated electric motor are known from the prior art and in particular from the patent literature. There are also companies that offer products for crank units and hub units as well. For example, on the right side, the design of a crank unit from a Chinese supplier with the structure from the left side is shown. And from the same company, a compact hub unit is known, which is again shown on the right side of this slide. This hub unit has a small electric motor with internal rotor and a planetary gear stage for a large ratio between the rotor shaft, which is connected to the sun gear of the planetary gear stage, and the wheel hub, which is driven via the ring gear. From plenty analysis of existing drive systems for Pedelecs, the idea arose to design an innovative and new drive system for Pedelecs with two electric motors, which are split onto a crank unit and a hub unit. The first motor in the crank unit shall be used mainly to support the driver, and the second motor in the hub unit shall be used to control different ratios in a continuously variable way. In principle, the idea is to use the technology from the Toyota hybrid system in a bicycle. The Toyota hybrid system has already been very successful in cars for the last more than 25 years. It links the crankshaft of a car and the wheel shaft of a car by a speed overlaying gear with a third shaft or ratio control shaft, which is driven by the second e-motor E2. This subsystem already offers a continuously variable ratio control, but it is usually limited in terms of output torque. Therefore, another first e-motor E1 operates with a constant ratio directly onto the output shaft. Without any shift system, the Toyota hybrid system offers a very big ratio range to drive small and mid-sized cars very efficient, because the two e-motors make all hybrid functions possible, like purely electrical driving and energy recuperation. In a still young state of the art regarding drivetrains for Pedelecs, there are already some proposals for such drive systems with an electric motor and with continuously variable electrical ratio control in the crank unit. The drive system shown here on the right side is a technological copy of the Toyota system in a special layout for bikes. It will definitely work well, but in this arrangement the crank unit becomes big and heavy. Therefore, again, the design idea is to design a drive system for Pedelecs with an ICAVP function by two electric motors, which are split onto a crank unit and a hub unit. Two smaller subsystems can be easier hidden between the pedals of the crank unit and in a small wheel hub. Another task is to lay out the system in such a way that in the main speed range above 15 kph, the boost power is transmitted almost evenly via both electric motors. The new two-motor system shall not be bigger and heavier than the conventional drive unit for Pedelecs with one motor plus the necessary multi-speed transmission, and shall offer at least the same driving performance. This central slide of this presentation shows the basic structure of the new Pedelec drive, which has two small electric motors in the full version. The first electric motor E1 sits in the crank unit and takes over the torque support for the driver, as this is known from conventional Pedelec crank units. A second electric motor, E2, is located in the hub unit and controls the ratio, but also provides a considerable part of the torque support. The two drive units are linked by a wrapping transmission like a chain drive or a belt drive. In this exemplary layout, its constant ratio is 1.58. In this crank unit, the crankshaft does not act directly on the output shaft via a freewheel F1, but by a planetary gear stage with a ring gear fixed to the housing. This gearing increases the speed of the crankshaft by a factor 3.5 and thus reduces the driver's torque by the same factor. This has two advantages. At first, the freewheel F1, which here is arranged between this planetary gear stage and the output shaft, becomes much smaller and lighter. At second, the driver's torque is now measured in the stationary housing connection of the ring gear of the planetary gear stage. The normally used torque measurement on a rotating part is replaced by a much more simple torque measurement on a non-rotating part. Moreover, the output shaft of the crank unit is already rotating so fast that only one further gear stage is required between the output shaft and the rotor of the first electric motor E1. Here a bevel gear stage is proposed which enables large gear ratios in a small installation space. In this example, this ratio is 7.1. Thus, the total gear ratio between the rotor shaft of E1 and the crankshaft is about 25. The freewheel F2 is omitted in this crank unit because a decoupling of the electric motor E1 is not provided. As in the Toyota hybrid system, the two electric motors E1 and E2 always work together via an additional speed overlaying gearbox, thus realizing the entire transmission function that would otherwise be performed by a multi-speed chain drive or a hub gear. In the hub unit, the stepper of the second electric motor E2 sits in a split axis and acts via a planetary gear stage with a fixed gear ratio of -7.5 on the ring gear, which in this layout drives the shaft 4 of the speed overlaying gear stage with 4 shafts. Shaft 1 of this speed overlaying gear stage is the drive shaft of the hub unit, which is connected to the crank unit via the chain or belt drive. Shaft 2 drives the rear wheel of the bike. Shaft 3 can be connected to the stationary axle and thus to the bicycle frame via a freewheel F2, which in this application has a different function. The 4-shaft speed overlaying gear stage is made from 2 linked 3-shaft planetary gear stages. The sum gears of both stages sit together on shaft 1 and have a common continuous toothing with the 54 Ts. The 2 planetary carriers on shaft 2 and 3 carry a total number of 10 identical planetary gears with 18 Ts. 6 of them in the planetary carrier on shaft 2 and another 4 in the planetary carrier on shaft 3. The 2 ring gears on shaft 3 and 4 also have identical toothing data with 90 Ts and can be made with the same tooling. Even the ring gear on the speed reducing planetary gear stage between motor E2 and the speed overlaying gear has precisely this gearing toothing, so that there is also a continuous toothing on shaft 4. The multi-mode drivetrain offers 2 driving modes whose characteristics are described on the right side of this slide. The first driving mode offers big constant ratio between all possible torque inputs and the output shaft 2 of the hub unit. The crankshaft plus E1 and plus E2 create independent from each other big wheel torques for strong accelerations or driving uphill on steep roads. The second driving mode starts automatically if the freewheel F2 is open. Then all relations of any speed difference of the 4 shafts of the speed overlaying gear stage remain constant. A continuously variable ratio can be controlled by the speeds of E1 and E2. Thus, the bike can be driven at nearly any crank speed which the driver currently prefers and choose via an app. In this driving mode 2, there are also constant torque ratios between these four shafts. In this layout, E2 provides 39% of the wheel torque, and E1 plus the driver provide 61% of the wheel torque. All the interactions of the subsystems, and in particular of the two electric motors in this drive system, can be explained in the best way by using a few simulations. This slide 13 illustrates this in a driving situation in which the required output power increases rapidly with increasing speed to 250 watt and then remains constant as shown in C. B shows the curves of the speeds on the crankshaft and on all four shafts in the speed overlaying gear. In such a speed overlaying gear system, all differences of shaft speeds are in constant ratios. At approximately 18 kph, all shafts in this subunit rotate with the same speed. Then the transfer efficiency is almost 100%. At bike speeds below 7 kph, the freewheel F2 is closed, or the speed of shaft 3 is controlled close to 0 RPM. The vehicle then starts off with an almost constant overall gear ratio. In E, the speeds of the two electric motors can be seen. E1 rotates proportional to the crankshaft. E2 controls the overall ratio, the cause of which can be seen in F. In this exemplary driving situation, also the driver supplies a maximum drive power of 250 watt. However, the driver does not increase his performance quite as quickly as the demand increase. Therefore, in C, an assistance power via E1 can be seen briefly in the range below 3 kph of driving speed, and this power comes from the battery. The battery power then falls back to 0 and the driver drives the vehicle on his own. In the range of a constant wheel power of 250 watt, the negatively defined output torque drops hyperbolically with increasing speed. As long as the freewheel F2 is not closed, the four torques of the shaft in the superimposing gear are in constant ratio as seen in figure A. In this main operating mode, which is driving mode 2, shaft 1 supports 61% and shaft 4 supports 39% of the output torque. The torques on shaft 1 and 4 have the same positive sign. T1 is made up from the driver's torque on the crankshaft and the torque of the motor E1. T4 is proportional to the torque of the motor E2. The curves of the torques TE1 and TE2 are shown in figure D. The two electric motors are relatively low loaded during this driving task. E2 only reaches its torque limit once for a short time at low speeds and maximum wheel torque. As long as the speed on shaft 4 is negative, E2 operates as a generator and drives the motor E1 via the double inverter system. Except from losses in the electrical subunit, the two powers are the same in terms of amount. From approximately 10 kph, E2 rotates at positive speeds and operates as a motor. Then E1 becomes a generator. In fact, such a drive system can also work without a battery. The respective generator then provides the electrical power for controlling the inverters and for the processor units. The electrical subsystem then only provides a continuously variable power split transmission. This slide 14 illustrates what happens in the drive system if for the same driving task and the same course of wheel power, the driver's torque and power are 0. Then the entire drive power must come from the battery as seen in C. In such a case, E1 is always the motor, E2 operates only below 10 kph as generator and otherwise also as motor. The system is designed in such a way that in the main driving mode 2 with open freewheel F2 and without a driver torque, both electric motors drive the vehicle with almost the same torque. At speeds more than 15 kph, which means in most of the operating points on nearly flat roads, both motors drive the vehicle with almost the same power from the battery. This relieves the two motors, or with motors of the same size as in other Pedelec system, leads to significantly higher boost power available for a short time. When driving off from standstill up to 5 kph, only these two electric motors can generate wheel torques of more than 80 Nm. At 20 kph it is still 59 Nm. This is sufficient for most operating points. At driving speeds below 10 kph the freewheel F2 can close. Then the crankshaft rotates with a maximum speed of approximately 90 rpm. If the freewheel F2 is closed, E1 and E2 can drive the vehicle independently of each other because reaction torques can be supported on the vehicle frame via F2. In this case, there is a torque ratio from shaft 1 to the output shaft of approximately 2.67 and from shaft 4 to the output shaft of approximately 1.6. Because both electric motors can generate their maximum torques at low speeds of up to 4.5 kph, total output torques of more than 180 Nm can be generated here. At 10 kph, the purely electrically generated output torque is still more than 115 Nm. Equipped with such a drive system, even a fully loaded heavy pedelec or a cargo bike can climb 20% gradients without any problems. This slide number 15 illustrates the system loads when driving a load cycle with such a 20% road gradient with a S pedelec and with a top speed of 34 kph. At the end of the cycle, an uphill gradient of 20% and a downhill gradient of minus 50% can be seen in Figure B. A bike with this multimodal drive system and with a driver with a peak power of 250 watt can climb up this steep road with a speed of 16 kph. Figure C illustrates the curves of the battery power and the driver's power. At the maximum incline, the battery boosts with more than 1.2 kW without overloading the two small electric motors. The utilization of the two electric motors can be seen in Figure F. E2 briefly reaches its power limit in two operating points. The overall efficiency of the power transmission reaches up to 90% as seen in Figure E. The electrical efficiency is lower and always falls to zero if the electrical system is currently not transmitting any power but is supporting torques. The battery power becomes negative if the system recuperates power. If the recuperation option is fully utilized, the driving range can be increased by 85% in this cycle. The next few slides, I would like to come back to some more information regarding the particular elements in this new drive system. This figure shows a typical frameless motor with a stator and rotor from the e-motor market. Many suppliers offer such motor components without diameters at the stators between 77 mm and 85 mm for the required maximum torque of about 4.5 Nm and for maximum rotor speeds of at least 4,500 rpm. This figure shows more in detail the layouts of the gearings in the multimode drivetrain. The maximum diameters of the gear wheels are similar to those of the e-motors. The bevel gear at motor E1 offers a big ratio in one gear stage. The planetary gear stages always have big torque capacities. In the hub unit, all ring gears have the same toothing layout. In the speed overlaying gear, also the two sun gears are identical. The multimode drivetrain uses two freewheels. The freewheel F1 in the crank unit can be designed as a very compact needle roller freewheel because of the low torque load. The freewheel F2 in the hub unit is designed as a Sprague freewheel with a high torque capacity. Schaeffler, GMN and other worldwide operating suppliers offer suitable freewheel coupling for these drivetrains. Here the full version of the multi-mode drivetrain is shown in a 3D design. The components of the crank unit, including the first electric motor, are very compact, arranged in a main housing with two covers. The components of the hub unit are coaxially arranged in a two-part housing. Let us now discuss a very compact light version of the multi-mode drive system. This is so interesting because it has only one e-motor but offers continuously variable ratio control and an automatically adjusted electrical boost. In this light version, the motor E1 is omitted and therefore the crank unit can be simplified a lot. The shaft 1 of the speed overlaying planetary gear in the hub unit is only driven by the crankshaft. The electric motor E2 has to support a torque proportional to the crank torque in the driving mode 2 with the ICAVP function. This constant torque ratio leads to a boost factor, which means the battery power, respectively the power of E2 in relation to the crank power, which increases automatically with the driving speed. This light version always needs a battery, because the one electric motor must always be active. But with today's battery capacities, this is not a problem, especially since the customers addressed with this drive system anyway want to use always some electrical support. If the electrical system fails, a purely mechanical transmission ratio remains in both versions of the multi-mode drive system. In this configuration, this maximum ratio is 1.206. With this ratio, the bicycle can be moved with high torques and reduced speeds. Slide 20 illustrates some boost factors at bike speeds above 8 kph in the power split driving mode 2 for nominal crankshaft speeds of 50, 60 and 70 rpm, which are achieved after starting at standstill of motor E2. The higher the driving speed and the lower the crankshaft speed, the faster E2 rotates. Then at the constant torque ratio between crankshaft and motor E2, the boost factor increases with increasing wheel speed and increasing wheel power, as well as with decreasing crank speed. This boost characteristic can also be adapted to different vehicle classes or driver requirements by means of the ratio of the chain or belt drive between crank unit and hub unit. For many drivers, it will be precisely this system layout that results in a pleasant driving experience with mostly well-suited electrical support. The boost factors, which increase automatically with increasing wheel speed, can be seen nicely in the simulation of an accelerated uphill driving up to bike speeds of 23 kph on a road with, for example, 4.5% road gradient. The graphics show again speeds in A and B, torques in D and F, and power flow in C, as well as the efficiency in the system in E. The driver has a nearly constant crank speed and therefore a nearly constant torque and driving power. In the light version, the torque of motor E2 is proportional to the driver's input torque, and therefore the torque of motor E2 is also nearly constant. Again, the boost factor is the ratio between battery power and driver's power. The simulations also show that with such an extremely simple drive system with only one motor and without any additional gearbox, it is also possible to drive the driving cycle according to slide 15. Only the maximum speed is slightly missed, and the steep incline must be driven in driving mode 1 at a maximum speed of 10 kph. With the same driver, a Pedelec with a light version of the multi-mode system needs about 21 seconds more to drive that cycle. But this is mainly due to the steep slope. Let me finally summarize the main aspects of my talk. The multi-mode drive system for Pedelecs is a drive system with 2 electric motors in the full version or with only 1 electric motor in the light version. Both versions provide an infinitely variable gear ratio adjustment in the main driving mode 2 and a driving mode 1 at low speeds with a big constant gear ratio for very large, partially electrically generated output torques. Both drive systems do not need any further multi-speed transmission. The overall system is divided into a crank unit and a hub unit. 2 smaller drive units can be integrated into the bicycle frame in a much more elegant way than 1 large and heavy unit. The big output torque is only set up in the hub unit. The chain or belt drive between the 2 units is only loaded with the power on shaft 1 of the speed overlaying gear in the hub unit. The torque of this shaft 1 is only 61% of the output torque. The inverters for the 2 motors are preferably arranged centrally near the battery and its control unit. Both versions of this drive system can recuperate via the electric motor in the hub unit. The full version of the new multi-mode drive system is suitable for trekking bikes, mountain bikes, pedelecs and cargo bikes, where high wheel torques and strong electrical performance are important. The light version of the new multi-mode drive system is the most compact stepless bike drive with electrical assistance. The crank unit has only 1 freewheel and the measuring system for speed and torque. The hub unit carries the electrical motor and 3 small planetary gear stages with many identical gear wheels. This makes it a very cost-effective drivetrain for many city bikes and other bikes that should not actively drive faster than 25 kph. The market for these vehicles is huge. Now, if you like to get more information about this drive technology, or if you like to test a vehicle with this technology,